off and your mic's on while Dan is speaking. Dan will probably speak for about 35 to 40 minutes, and then afterwards we've got time for questions. I suggest that you post your questions in the comment box, and then I'll summarize the questions and have a conversation with Dan. And I think maybe we'll invite some of you in to ask questions, but it's probably a bit disruptive to have an open mic here. So I don't know whether Dan does need an introduction, because he had a long and illustrious career behind him at MIT, working on many different issues that he is talking about, from manufacturing to design processes. Many people in the audience will probably know him from his work on design structure matrices. So I'm very much looking forward to how Dan portrays his career. So I think over to you, Dan. So if you want to share your screen. We still see you, so we still need to share the screen.
I know, I'm looking for it. There it is. Well, what happened?
It's perfect. We can see it very clearly now.
Okay, I cannot see it. Now I can see it. Can you see it?
We can see it, yeah.
Okay, so good morning, good afternoon, good evening, wherever you are in the world. It's my pleasure to give this talk. Thank you very much to Claudia for setting it up. I'm going to talk probably for about 40 or 45 minutes, and I'm going to give you a little preview here of all the controversial things I'm going to say. A lot of design research is about the behavior of individuals creatively making up a design. I believe that design is a culturally and socially defined activity carried out by groups of people, more so than a creative act carried out by an individual. Another controversial thing, you may have thought about modularity. I believe that there is no such thing as modularity. It's a very attractive idea. I'll talk about more later. Nearly all innovation is incremental. There are apparent spectacular counterexamples, but I think it's mainly incremental. Even Isaac Newton said, if I can see far, it's because I'm standing on the shoulders of giants. Designers spend more time identifying failure modes and resolving conflicting requirements than they do on conceptual or detailed design. I know this from personal experience. I've also discovered that some of the best thinking on product development, which contains design as a subset, is being done by management science researchers rather than engineering design researchers. I discovered this in the middle 1980s, and I began doing things like writing articles for the Harvard Business Review. And so I have a rather different view than maybe some of the technically based people in design and design research. So I'm going to talk very quickly about my career. I have 2 bachelor's degrees, one in engineering and the other in history and literature. And I depend a lot on my interest in history to understand the history of technology, the history of companies, the history of design and science generally. I've been influenced a lot by industry visits to companies, particularly Japanese manufacturing and design methods, very influential. I started out in robotics. I'll talk about that very briefly. Robotics led me to robot assembly, then to assembly entirely. And assembly is a very intellectually challenging and interesting topic. It's very integrative. It brings together parts and people and companies, and it spans all of product development. I'll talk just a little bit about the history of design research, not very much. Discuss sub-assemblies, modularity, and outsourcing, all of which are linked, and the integrative force of technology, the fact that technological things are linked to each other, and how this sort of invalidates the idea of modularity. This is a picture of me in 1969 in the New York Times Magazine, the only time I've made it that far. My PhD thesis was sort of a dead end in the sense that it was computationally very expensive. And I turned to mechanical arms and prostheses, artificial arms. There was work in the mechanical engineering department at MIT, put an electric motor into the elbow in an artificial arm, and an amputee could run this arm using sensors that were applied to the skin. And when he flexed the muscles, the motor would react. And I turned my attention then to the problem of controlling an arm where all 6 joints were controlled by motors. And how would you send signals to all 6 motors at the same time? And when you're doing a purposeful action like reaching outward, the motors all have to run, and they have to run at particular velocities, and those velocities change as the arm moves around. And I figured out how to program a computer to calculate all these velocities so that if you gave a signal saying reach outward, the arm would reach outward. But then the question became, how would an amputee give 6 independent signals, even if the computer was able to interpret them? One signal to reach outward, one signal to lift upward while keeping the cup of coffee level. And I decided that amputees would have a hard time doing this. And I can say that half a century later, people are still working on this problem. And they've gotten to the point now where they're trying to put implants inside people's brains. So this remains an unsolved problem, essentially. And I walked away from it. And what I did was to shift to industrial robots, where there's a computer that figures out all of these signals and says, I want the arm to reach outward. And then the other part of the computer computes the different velocities. And NASA adopted this for control of the space shuttle robot arm, and later on, I'm pretty sure, for the space station robot arm. So my work has gone out. I didn't have anything to do with it. NASA found my paper and put it to use. But it got me into industrial robots. I went to work for the Draper Laboratory. I left MIT. And people were very worried about the rising strength of Japan, its manufacturing capabilities, product development. And the US government got interested, and the National Science Foundation began to support research in manufacturing and design. And we got some grants from the National Science Foundation, and we worked on robot assembly. And I'm going to show you a picture here for a second. This is work we did. We assembled a complete automobile alternator in 1976. We programmed the robot. There was a control system with software. We taught the robot to work. The robot changed tools in the process of doing all of this work. And we wrote an article in Scientific American, and people read that article. And we got inquiries. Is our product ready for robot assembly? And we said, let's see if your product is ready for assembly at all. And then we'll see what assembly method is best. And this got us into all kinds of stuff. The assembly process is extremely interesting, and designing products with their assembly in mind gets you into all sorts of other stuff. We had to find out how many of these units the company wanted to make every year. How many different versions did the product have to have? Did they want to upgrade the product? How soon were they going to introduce variations? And so we not only got into the technical issues, like the assembly sequence and partitioning the product into subassemblies, but then trying to understand what was the right assembly method, including how much it would cost to do it by each of different methods. And one of the things we did was to develop an economic model of robot assembly. This hadn't ever been done before. And we decided that robot assembly was not going to be easy to justify economically. And this was kind of a jarring conclusion, because everybody was very excited about using robots to do all sorts of stuff. And people, in fact, are very, very good. And it's very difficult to do what people do, to do it as fast and as dexterously as they do, with all of the other oversight that people can exert while they're working. But assembly itself turned out to be quite an interesting topic. And even if you weren't thinking about robots, and ultimately I walked away from robots too, except for some work in the 1980s on robot grinding, and turned my attention more and more toward the assemblies themselves. So assembly is this very integrative process. And the CEO is involved because he's deciding what markets to put this product into and how many to make each year and all this other stuff, different versions for different segments of the market. And then there's also the factory floor part where you actually have to put these parts together. And you also have to get the parts from someplace, and supply chains are involved. And no other manufacturing process spans all of these different aspects. It isn't true of grinding, it isn't true of drilling or milling or applying plating. Assembly has this span all over the processes of creating and developing products. And assemblies are actually complex systems. And my Draper colleagues and I were all basically systems people. And even though not one of us had a lick of experience or education in manufacturing, engineering, or industrial engineering, we knew what to do when companies brought us their products, and we ended up telling them things about their products that they didn't know. And so this pushed me and my colleagues more and more from the technical aspects into the managerial aspects of robotics and assembly and manufacturing. And my academic colleagues shifted from being in engineering schools to being in management schools, and my publication shifted from technical journals into management journals. And I don't know if I had stayed in artificial arms or something like that, that I would have come to the appreciation of what managers do. And maybe sometimes engineers don't appreciate this. But as I learned more and more about this other stuff, about the economic aspects and the organizational aspects, it got more and more interesting to shift in that direction. So while I was at the Draper Lab for like 19 years or so, we had consulting clients from automobiles, aircraft, ships, gyroscopes, every way you know of measuring angular rate. Sewing machines, hand tools, sewing machines themselves are a fascinating type of product. They're the first complex product for the public market. And they're still being made, of course, all over the world. Very, very interesting history. The machine tool industry had to be created in order to serve the sewing machine industry. All the machine tool companies in Connecticut surrounding Greenwich, those are all companies that came into being to serve the sewing machine industry. Up until like today, I'm still going to factories. I've been to hundreds of factories making all sorts of stuff: cameras, machine tools, disk drives, sewing machines, ships, aircraft, you name it. I've just been to hundreds and hundreds of factories all over the world, and it's really fascinating. The stuff we did at MIT after I got out of the Draper Laboratory, product development in the car industry, a productivity study of automobile engine plants. I went to 27 different engine plants. And for engines, there's essentially one best way. The notion of one best way goes back to Frederick Taylor, the beginning of management science in the early 1900s. But I also looked at car doors, and car doors are fascinating. There is no best way. Every car company has its own way of designing and manufacturing its doors, and I can tell you every company thinks its way is the best. And I've written research papers about this as well. The work at the Draper Laboratory involved all kinds of fascinating products. And we developed the idea that there was a particular design challenge from products that we called complex electromechanical optical products. And our definition was multiple technologies all packed into a small space. And we had two exemplars, one that we presented to our Defense Department clients and one to our commercial product clients. The one on the left is a missile seeker head. It has a big rotating mirror on a 2 degree of freedom gimbal, and it can nod up and down and scan left and right, and this mirror spins, and the light path comes onto this big spinning mirror first, and then it bounces forward to a convex mirror, which is not mounted so that its optical axis is on the spin axis, but instead is slightly off axis, and paints a Lissajous figure onto an infrared detector, which has to be kept at minus 94 degrees. So there's a Dewar flask inside this thing, and it all has to fit inside a 4-inch diameter. And on the right is the original Polaroid SX70 camera with the classic pentagonal optical path that you have inside the mirror of a single lens reflex camera, except this thing folded up flat and there was no air inside. The film is a chemical factory. There's a computer inside. There's electric motors and gears. There's an acoustic system for range finding. It's amazing, and all for $100 or something. And the challenge basically is a quote at the bottom of the screen. I heard a guy say this in a meeting: "I'd give my wife for 1/10 of an inch." This is where they are in trying to design these things. The thermal problems and vibration and electronics and electromagnetic interference, you name it. Why are these things so hard to design? That's where I was, and I still am. I was taught in the 1960s that design is lots of different things. It's creativity. We had brainstorming sessions. It's resourcefulness. Somebody hands you a shoebox. It's got 2 rubber bands, a hair dryer, a ball of string, of 5 paper clips, and you're supposed to design a gizmo that'll climb a rope and whistle "God Save the Queen." Design is drafting, making mechanical drawings. Design is rendering, making pretty pictures of things. Design is computer optimization. You give the computer your specifications and the computer comes back and tells you what to do. Design is none of these things. It may involve them from time to time. That's not the core. The core, as far as I can tell, involves understanding constraints. The customer says to you, it has to weigh less than this, it has to cost less than this, it has to fit inside a box smaller than this, it has to use less than this much energy. And when you put all the constraints together, it's infeasible. There is no design. And so you have to crawl your way out of this by negotiating back to the customer. And a student and I wrote a computer system that would take a computer model of a design and allow you to maneuver the constraints, to explore what would happen if you violated this constraint, if you violated that constraint. How do you negotiate? How do you tell where to push back in order to create a design space that's actually feasible? Another thing that occupies designers is finding what we came to call the design drivers. Design drivers are decisions that you make that make it impossible for you to make other decisions, that those decisions have been made already, and you don't realize it until you identify the design drivers. And the best example I have is Henry Ford's assertion they can have any color they want as long as it's black. And well, that's Henry, you know, he's just stubborn or whatever, or he controls the market. But no, that isn't the reason. The reason is that in those days, cars were painted with lacquer, and lacquer takes a long time to dry. And black apparently dries faster than most other colors. So if you want to make 1 million a year, you can't wait 2 weeks for the paint to dry. And so It turns out that the design driver is the decision that you're going to make $1 million a year. And after that, you discover that you don't have your choice of colors. And that's the design driver. Finding and mitigating failure modes, that's another thing. Anytime you fix a problem in a design, you create another problem, and you hope that the new problem is smaller than the previous problem, but you don't really know. And somebody said to me once, design is 100 people in a room screaming at each other. And that may have more truth to it than a lot of other stuff. And there isn't a lot of research about that. That's one of the reasons why I got into the design structure matrix. I'm not going to talk about it because you all know about it. But the problem of finding out what is happening during a design process was so fascinating to me. And I knew about the design structure matrix going back to very early publications of it in the early 1980s. And was hoping that it would find broader use, and indeed it has. So the question of where products come from, how they're designed, what is the process organizationally, we all realize now that the technological complexity drives manufacturing and design into specialties, and companies get good at pieces of this. And there's an entire supply chain for products, and there's an entire supply chain for factories. All the equipment that goes into factories, there's a supply chain for that as well. And so you have these cooperative chains and groups of people and companies. And when you have this kind of thing, like 5,000 people involved in designing an airplane, for example, people can be too creative. And you try to discipline the design process. I interviewed people at different companies about this very thing, and they said that when they analyzed situations where they had had trouble with a product launch, they were able to trace it back to a place where some designer somewhere had not followed the process, or had pushed the design outside the envelope of known performance. And so they had to practically make a lockstep, check this box, check that box, check the other box, in order to make sure that the product came out right. And this is stifling, of course, to people who want to be creative. And it also poses a challenge, I think, to people who study the creativity of individual designers, because that role is going to be challenged when such people get out into the real world. So design is a social construct, and this is a concept, of course, from social science, about which I know only a very little, but I do know that every company has its own design and manufacturing culture. And there's situations where a company totally will not do a certain thing. We'll never do that again, kind of stuff. We've visited companies in the same industry, different companies, and one of them will say, "Oh, such and such is impossible. We tried that years ago and it didn't work." And we, having visited other companies, know that there are other companies that not only do this, but they do it every day, and they've done it every day for years. And because of our non-disclosure agreements, we can't tell these other folks that they're shying away from something that really is possible to do. A lot of work I did involved going around to companies and interviewing people. And one of the companies I went to many years ago was Ricoh Camera in Japan, and I was pursuing the issue of subassemblies. And I said to them in this camera, "How do you decide the subassembly boundaries?" And they said, "Oh, it's a done deal. There are 4 subassemblies: the shutter, the autofocus, the mirror box, and the film transport." So here I am in the middle of an interview, and I run into a brick wall, and I can't pursue the idea that I wanted to pursue. So I had to regroup. And I knew a little bit about shutters. I had hired a guy who used to design at Polaroid. And so I said, "Gee, shutters are pretty complicated. I suppose you've got somebody who's your shutter expert." And they said, "Oh, no. On one camera, he'll design the shutter, but on the next camera, he'll design the autofocus. On the next camera, he'll design the mirror box. On the next camera, he'll design the film transport. And so for them, knowledge is distributed throughout the group. It is not a set of specialists. I visited Toyota. I know a fair amount about how Toyota does things. In the process of studying car doors, I learned that there was a production engineer who knew more about car door design than anybody else in the company. The production engineering department produces the factories. They design the assembly lines, they order the machinery, they are basically run the company. The production engineering department runs Toyota. No other company I know is like this. Most car companies are run by the styling department, but not Toyota. The production engineering department runs Toyota. So when you have supply chains, you have dependency, and companies get involved with each other. And economists are the people who have studied this kind of thing, and they've come up with terminology like hold up, for example, or exit and voice. Exit means you simply walk away from some sort of agreement, and voice means you have a cooperative agreement between different companies. And economists have come up with this stuff. So I've found people at business schools to talk to, and I've got their names listed across the bottom, and there are many others, of course. But these are the people I thought were doing the creative thinking in all of this very complex stuff. And so I got interested in outsourcing particularly, and it's driven by technological specialization. And the design theory community thought about modularity, and in the management science community, they thought about core competence. And these are different words for the same thing in a sense, and they come down to the question of what do you do and what does somebody else do? And in economics, this is called the theory of the firm, and somebody got a Nobel Prize in economics for that a few years ago. At General Motors, which is a highly politicized company, you couldn't use the word modularity because it really meant outsourcing, and you just didn't want to use the word outsourcing because that was really politically dangerous. And some of the confusion on the technological side comes from a confusion between subassemblies and modules. A subassembly is a collection of parts that performs a function, and you can test it to see if it does that function properly. You can't test parts, you can inspect them. Parts don't do anything. Only subassemblies and assemblies do anything. So you test subassemblies and you inspect parts. And modules are different conceptually in the sense that they're supposed to be independent of other things. Nobody said a subassembly had to be independent. It only has to be a collection that holds together in the shipping box, and you can test it and see what it does. But modules were intellectually different, and the idea was that because they're independent, you have all kinds of advantages, like you can design them separately and put them together. In the world of economics, people thought that you could advance innovation more quickly because you didn't have to worry about changes that you made in one module separately from the others. And this also brought people into the notion of reuse and carryover. And there was a lot of design theory thought about this. And the thought was that this would reduce risk, it would reduce cost. I've had personal experience with this, and very often it does the opposite. It increases risk, it confuses product development. There are always hidden, forgotten, or obsolete assumptions baked into some of these things. You carry them forward, and they cause trouble. There are past attitudes, conditions, and technologies, and these are carried forward, and you don't know where the tentacles are. I have lots of examples. I don't have time, I'm sorry, but it's really possible to get in trouble by using old stuff. The people who designed them are gone. Some of the tooling is gone. In some cases, you have to go to a new supplier. The supplier knew something you didn't know they knew. But in thinking about outsourcing, I worked on this with colleague Charlie Fine in the management school at MIT and worked out a 2x2 matrix like this, trying to understand what were the conditions for being safe in outsourcing. And you can't separate it from a concept in system engineering, which is essentially the same as modularity, decomposability. Can you actually take the thing apart without cutting all kinds of relationships? And the other issue is from supply chain theory, the notion of dependency. And we worked out the idea that you could be dependent for capacity, which means you could do it, you just don't want to bother, or you're dependent for knowledge because the supplier knows something that you don't know. And if the outsourced item is decomposable and you're dependent for capacity, you're in good shape. It's a light bulb, it's a screw, something like that. But if you're dependent for knowledge and the outsourced item is integral, you're in terrible trouble, because now you don't know when the supplier is going to do something that's going to make your product stop working. And this can happen in many circumstances. And I tried to work it out this way. 2x2 matrices like this are very common in management science. And that's a motif, so to speak, that recurs. Just a little bit of an example here. Taka Fujimoto did his PhD thesis at Harvard Business School on the question of why Toyota was able to design automobiles so much faster than anybody else. That wasn't the only thing his thesis was about, but this was a major issue. And he found that creating stamping dies was the critical path. And Toyota was able to do this in a few months. And why was this? Well, one of the reasons why was that they kept control of the entire process of making the dies. They made them themselves. They didn't have other companies make them. And they cut the dies on their own machine tools that they made. And they had rigged these machine tools up with temperature and strain sensors so that they could cut faster and cut more accurately. And Toyota also makes all the machinery for its engine plants. And so they've decided to insource certain things that are critical for letting them develop their products, and they can outsource other stuff that isn't as critical. And Toyota's thought more about this kind of thing, I think, than a lot of other companies. Modularity has to take its place in other concepts that are important in innovation. Rebecca Henderson did a PhD thesis again with Kim Clark at Harvard. Rebecca is an MIT graduate in mechanical engineering, and they came up with another interesting 2x2 matrix trying to understand innovation. The problem was that certain companies got knocked out of the market by their competitors. And when the companies took apart the competitor's product, the product had all the same pieces of it that their product did, but their product wasn't as good. And the question is why? And what they came up with in this study was that in addition to the traditional notions of innovation, that innovation is either radical or incremental, they came up with two others they called modular and architectural. And architectural is particularly interesting one because it means rearranging known modules. For example, the front-wheel drive car compared to the rear-wheel drive car. And what's fascinating about this is that without developing new modules, you can develop something new. And if this is true, then modularity by itself is not a strong idea. That if there were no interactions, so to speak, then why would plugging the modules into different combinations produce something that was actually innovative? And yet this has happened. So I was impressed by this whole concept when I first encountered it. This dates from the early to middle 1990s. Henderson, I think, was the next main PhD student at Harvard for Kim Clark after Fujimoto. So modularity and outsourcing exist. They have been tried and used. Very strange things happened. The PC industry turned out to be dominated by a supplier instead of by the system integrators. In the car industry, the aircraft industry, the industry is dominated by the system integrator at the top. But the personal computer industry is dominated, or has been, by Intel from the early 1970s right up until last week, essentially. And this overturns everything that you would think about supply chains. But attempts to simplify design by advancing one module at a time failed due to these hidden interdependencies. There are companies like GM and Ford who divested their component divisions, and their design process lost coherence. It lost efficiency. You have competitive leakage. The suppliers start giving their knowledge to other companies, and outsourcing evolved into offshoring. And now we're seeing this happening more and more. And outsourcing may be an intermediate phase between vertical integration in the West and vertical integration in China. It may happen. It may take another 50 years. I don't really know. So when does modularity work? It does really work when energy is really information. If energy is really useful work, horsepower, lots of horsepower, then modularity doesn't work. It's only when energy is really information that it works. And asked another way, why is mechanical design so hard? I got tired of whining, basically. The Draper Laboratory made a proposal to DARPA to study the design of these complex electromechanical optical products. And DARPA said, forget it. If you guys were smart, you would do things the way the semiconductor people do. They have pre-designed component libraries, and they plug and play, and they get all these wonderful products. And I wrote a paper called Why Mechanical Design Cannot Be Like VLSI Design. And you can read that. I wrote that 20-odd years ago, 25 years ago. And the difference is the mechanical items operate at very high power levels, and semiconductor products operate at microwatts and picowatts. And if you have a logic system in electricity, anything between 0.5 volt is a 0, and anything between 4.5 volts and 5 volts is a 1. That's a 10% tolerance band. There isn't a mechanical item that I know that will operate properly with a 10% tolerance band. Think of a jet engine rotor his center of mass is located 10% of the diameter away from the spin axis. You get that up to 10 or 20 RPM and it'll explode. And these things are supposed to run at 50, 60, 70,000 RPM. So in high power systems, you have a source and you have a load. And the way to maximize energy or power transfer from the source to the load is to balance the impedance. Each one has an internal loss. There's a loss inside the source, there's a loss inside the load, and those two losses are supposed to be equal. And in VLSI electronics, they fail impedance matching on purpose. The impedance are mismatched by 10,000 to 1 or more. And this allows you to plug them together. And the source doesn't know that the load has been attached. And so you can develop these single purpose things, and you just plug them together, and you get what you want, and it's remarkable. But it works only in that context where you have only one thing happening, and you don't have all the multiple stuff. Mechanical design is multimodal, and it's all about interactions, which is, of course, the enemy of modularity. So this brings me to the end. I hope I've shocked you sufficiently. To understand design, you really have to do some design yourself. You can't stand back and see what's going on. You can't ask people enough. You have to do it. The technical and managerial aspects interact and interlock very strongly. One of the blessings we had from our early National Science Foundation research was that we had advisors from industry, and we met all kinds of fascinating people. And one of the things they said to us was, you have to understand the economics. And as I said, we were the first to write an economic cost model of robot assembly, and we learned quite a lot from that. You have to understand the differences in the challenges between the individual creative designer and the member of a team designing a complex product, especially a distributed team. You need some historical perspective. I've been at different companies. I've worked at different companies. They each have their list of no-nos. They have their vocabulary, and it's all historical within the company. You have to learn to avoid technological determinism. Things happen sometimes by accident. Culture, social attitudes, history, and norms will affect what technologies are adopted, what decisions are made. And it didn't have to happen that way. Thomas Edison did not invent the light bulb. He invented the first light bulb that didn't burn out after 10 minutes. Elias Howe did not invent the sewing machine. There are sewing machine patents going back in France, especially 20 or 30 years. Elias Howe invented the first submarine sewing machine that didn't tangle up its thread. And so that's when things happen, is when you get the idea to actually work properly. And finally, just an advice to young people, you need to know when to walk away. I've walked away several times. I gave the example of the multi-joint prosthesis. 50, 60 years later, people are still beating on this problem, and in the meantime, I've had 3 careers or something. I don't know. Anyway, this brings me to an end. Claudia, should I stop sharing my screen? And how do I do that? Yeah, okay. So I'm ready for questions.
Thank you very much, Dan. This was absolutely fascinating. I'm sure there are lots of questions for you, so I suggest that if people have got questions, put them into the comment boxes and I'll ask them, or I'll call you with the questions. But maybe while everybody else is thinking about their questions, maybe I can ask you something. I was very intrigued by your comments on design creativity. And I was wondering whether what you actually meant by creativity, or because I'm often wondering whether the notions we have of creativity as being essential novelty and being far away from starting points is appropriate to engineering. And I wonder what your thought would be on that.
Well, an awful lot of engineering is routine, actually. And it has to be routine because you have to be extremely careful not to do something that causes unknown problems. Things are very complex. And this is a conflict that senior managers have expressed to me many, many times, that there's a constant conflict between trying to inspire their engineers to think creatively and at the same time make them follow the rules. And so there's a lot of design research about how people come up with ideas or concepts, and it's not the main thing that engineers do. And this is a divergence in some sense. Maybe I'm not answering your question the way you asked it, but coming up with new stuff is something that just doesn't happen very often, and people are working very, very cautiously to make sure they don't make a huge mistake. A current example outside all of our fields is this vaccine for the virus. People say we came up with this vaccine in 9 months. Well, people worked, I think, 20 years to come up with the technology that was then applied. And this technology allows you to design a vaccine, which nobody ever did before. Nobody ever designed vaccines. Vaccines were always discovered. They are accidents of nature. We heard a lecture from people at the University of Washington Medical School, and I don't remember all the details, but this is the main point he made, that vaccines up to now have not been designed. They have been discovered. They have been found in nature. They're the virus itself. And so this is totally new, and yet it's 20 years of development.
Okay, no, you didn't quite answer my question. I was partly wondering whether we capture the creativity of engineers in our understanding of creativity.
Well, I guess I don't know. I guess I still don't completely understand the question.
Okay, I think in that case, I should probably not take this off on a private sideline. We have a question from Andreas Hein, who essentially said he really liked your paper on the mechanical design versus VLSI design, and is wondering what you think has changed since you wrote this paper.
Well, there was one thing in the paper that I hinted at, I was aware of. The paper, of course, is quite old by now. But the basic premise was that you could violate the principle of impedance matching without having to worry about the loss of power. And even at that time, people were worrying about how hot microprocessors were getting. And it turns out that controlling heat has been the barrier to further development of microprocessors, whereas it used to be thought that it was Moore's law, that you couldn't make the pattern smaller. And in fact, people are still making the pattern smaller even now. And yet the problem is that you can't get rid of the heat. You can fry an egg on these things. And so what they've done is to redesign them so that there are multiple processors inside a little box, and they're able to keep each one of them cooler. So the problem of energy loss has in fact become paramount. And my idea was that it was because you could ignore power loss that you could do all these lovely modular things. I do think you can still do those modular things, but now you do have to worry about energy loss. It's really big. It's really changed how the semiconductor industry works and what it worries about. That they're still able to conquer the problem they thought was going to beat them, which was Moore's law.
And what about the more generic point? Because you gave a technical answer to those differences, but do you think that there is a different capability of different industry sectors to take up modular design?
Oh, I think modular design still belongs in the low power world. I think that you can't design an engine without knowing what transmission you're going to attach it to, for example. You can be modular in some things if you obey specifications. The 737 aircraft can be equipped with more than one jet engine. The 787 can be equipped with engines from 2 or perhaps 3 different companies. But the designers of those engines had to adhere to a common set of specifications. And the main issue with the engines is compatibility of the control systems, the fuel systems, and then the physical attachment points where you stick it onto the wing. You can swap an engine off a wing in about 30 minutes. It's quite remarkable. And you can put a different manufacturer's engine on, although I'm sure you have to make other adjustments elsewhere. But that's been heavily controlled by huge specification and interface control documents. So it can be done in the high power world, but you have to do it pretty carefully. You can't take a Chevy engine and put it into a Ford car, even if the engine mounts are compatible. So there's a lot of places where this stuff still doesn't work, and everything has to be tuned and controlled. And I think that's going to continue basically forever. I think that the notion of impedance matching and other facts, the fact that mechanical systems at high power have side effects at the same power level, those are things that are going to persist. I remember somebody saying to me when I was talking about this problem years ago, he said, "Oh, you can stop bad information. You can stop it a lot of ways, error correcting codes, for example, but you can't stop vibrations propagating across a physical structure."
Thank you. Yes, we have got a reply or comment on this from Stephen Eppinger, who says, it's clear that pure modularity is a fanciful notion. It is a tremendous high degree of connectivity and integration, also a ridiculous idea.
I'm trying to read it here. A fanciful notion, a tremendously high degree of. I'm reading it. Is a tremendously high degree of connectivity integration also a ridiculous idea, or is there a need to continue to strive to achieve this? We rarely see highly integrated designs in practice. I think that's probably true. There's tremendous danger in all of this. Just to mention the Russian computer hack that's been revealed in the last few days. The internet is the ultimate in interconnectivity, and people can get inside other people's trousers, basically. It's just remarkable. And yes, I do believe that ridiculous may not be the word I would use, but there are all kinds of hidden dangers, absolutely.
So I suppose that neatly links to Warren Searing's questions. How can we make mechanical design simpler then if we can't have modularity and we can't have too much integration? How do we make it simpler?
Well, I think you proceed incrementally. I don't know that any other way. You take baby steps and you see if they work. I suppose that's always true when you're presented with extremes, that you try to find some place in the middle.
I think we also had a couple of questions on outsourcing. One was looking at you talked about outsourcing externally, but of course in large organization you have got silos internally. What is the danger of the internal outsourcing?
Well, I suppose you have that as soon as you have a product which is too complex for a single person to design working alone. As soon as that person has to work with a second person, you have internal outsourcing. Maybe that's carrying it a little bit to an extreme, but then people have to dialogue. There has to be communication. There's going to be trial and error. The outsourcing outside to another company risks the additional problem of cultural mismatching. And I don't have examples particularly at hand for that, but I know that the internal cultures of companies are very different. What do they value? Who gets promoted? What's their method of working? I worked for the last 7 years, from age 70 to age 77, remarkably, luckily, at a company, and it had its own internal cultural problems, things you couldn't say, mistakes that other people had made that they hardly talked about. So you put your foot in your mouth right away without knowing it, because you didn't know what it was that the other people were afraid to talk about. But one of the things I learned was that they had no use for my main skill, which was engineering analysis. They didn't have any confidence that you could do a mathematical analysis and computer simulation of their product. Their entire modus operandi was trial and error, and they just didn't dare do anything else. And the result was that they didn't understand. They got the product to work, but they had no idea how close to the edge they were, because they had no models. And the result was that one of the main activities they had in this company was problem-solving teams. And they made an expertise out of problem solving because that's what faced them all the time. They had failures in the field all the time. And it was just remarkable. Which way did they go? Instead of engineering analysis, they went to problem solving. And you know, what's life like in a company like that for somebody who's a graduate of MIT? It's a real mismatch.
But you still seem to have enjoyed it, or?
I was fascinated. It was marvelous. I learned all kinds of stuff. I got qualified in working in a blood lab, which, you know, a mechanical engineer doesn't normally work in that kind of thing. But this company made equipment that analyzed blood, and the employees donated blood so the company would have blood for testing its equipment. It was fascinating.
But that's also an interesting mismatch between something that maybe doesn't have the best processes, but still people enjoy working for the company.
Well, they tolerated me until they didn't.
Okay.
One day they said, Dan, we're not renewing your contract. Goodbye. And that was around the time we had decided, excuse me, to leave Boston and move to the West Coast anyway. So the timing worked out all right.
Well, I'm glad to hear that it worked out for you. We had a follow-on question from that on the rise of automated design, decision-making, and generative design, and whether that is a form of outsourcing in which you see some promise.
From automating design?
Yeah.
Well, let's see. First of all, I don't see a connection to, excuse me, I'm sorry, to outsourcing, but it does refer to a kind of design where the problem, sorry, I'm getting hoarse, where the problem is so well understood that you can mechanize the steps. I'm sure in the design of many complex things, there are portions of the design that are given to algorithms for optimization of various kinds. I'm sure the layout of VLSI chips can be automated to some extent. Originally, it was thought that they could be completely automated, and it turned out that you didn't get efficient use of the space, and the people had to adjust the designs. But you can get an awful lot out of certain algorithms that will get you partway through. There are certain procedures that keep you from producing a design that violates regulations. For example, when you design the windshield of an automobile, you have to allow a certain amount of visual space, and there can't be obstructions to the driver's line of sight and visual field. And there are algorithms that will help you to design a windshield or a visual opening that meets the regulations. And there are others where you really have to have the design right, or else you can get into legal trouble. And so those are places where an algorithm is definitely helpful. But for producing the entire design, no, I don't think so.
I suppose the question might also have been aiming towards the sort of robots as colleagues and intelligent agents in design that is being discussed as one of the big trends.
Well, of course, I think that backs it up one step to designing the robot.
Yeah.
Or to designing the, you know, and so it's tough. People are very good at what they do, and it's not only in mechanical assembly, but in thinking. And people were discovering, of course, this is commonly known, that facial recognition or other kinds of algorithms have hidden biases in them. And how do you test for those things? We're worried about this with testing the vaccines recently. Are there subgroups of various types that might react differently to the virus, to the vaccine, I'm sorry, and have we adequately tested it and make sure that it's safe, that it's effective? It's tough. It really is, and people are brave. When I first went to the company that makes these blood instruments, I said, you guys are brave. I have tremendous respect for you. People's lives are in your hands, and you're willing to go out there and make this equipment. It is spectacular.
Now, thank you very much for all your answers and your questions. I think we've covered the questions in the comments. I think just as a final question, having listened to your talk and all the things you commented on, you've been at this for nearly 60 years. And I'm wondering whether you have the sense that we are actually making progress and we are actually getting better at that, or is the complexity of the product outrunning our ability to support the process?
Well, I think that progress creates its own problems, and the problems create their own process.
Yeah.
Progress. If we weren't trying to do better, then we could just get more and more skillful at what we do. And I think there's always going to be progress and new ideas. There was a time, of course, 500 years ago or more, where progress was frowned on. You were supposed to leave stuff alone. If you go back into the history of science and history of culture, particularly in Western Europe, which we've studied quite a lot in this part of the world, there was a breakout. Before that breakout, you said what Aristotle said, and that was the end of it. And you weren't supposed to mess. And the Greeks had the myths of Prometheus, where you get too close to stuff that belongs to the gods, and you get smacked down. And the idea of progress is a relatively new idea in the last several hundred years. We don't realize that. We just accept the idea of progress. I think we're entering a period, maybe since the development of the atomic bomb, where people are not so confident that technological progress is good. We've thought that for several hundred years. It's done a very good job, and people's attitudes may be changing. The genie's out of the bottle, and we're struggling to put it back in. I wish we could abolish Twitter. We can't abolish Twitter. We can't abolish the tweeters either. And so we're stuck with it.
I think before we get into any of these really, really big questions, Dan, we should probably thank you again for your talk and end the official seminar and let everybody go. So thank you very much for attending the talk. We seem to have had a very good turnout, and we'll have more of these talks in the new year. I'm in the process of organizing them, so watch the space.
Bye-bye. Thank you.